Hello everyone, I am Mallak Basheer from the Department of Electronics and Communication Engineering. My topic for digital image processing assignment is nonlinear image sharpening using the gradient. For a function, the gradient at coordinates x comma y is defined as the two-dimensional column vector grad f given as partial f by partial x, partial f by partial y. As this is a vector, it can be characterized using magnitude and phase. Magnitude is given as root over gx square plus gy square, and phase is given as tan inverse gy by gx. Magnitude gives the change in intensity of a pixel at the point x comma y, and phase gives the direction in which the change of intensity is maximum. Calculating square root using the hardware is not computationally effective, so instead of doing that, we generally calculate gradient using this simple formula, which is mod gx plus mod gy. For images, to calculate gradient, suppose if you want to calculate gradient at position p1, at pixel p1 of this image, then we keep this kernel at this position to calculate gx. We multiply -1 and p1, 1 and p3, and we add these two, then we will get mod p3 minus p1. Similarly, to calculate gy at p1, we simply keep this kernel here and we multiply corresponding pixels, then we will get mod p2 minus p1 as our gy. To calculate resultant gradient, we add mod gx plus mod gy, then we will get mod p3 minus p1 plus mod p2 minus p1. Extending this concept, we have Roberts operators. When diagonal edges are of interest, then we use Roberts operators. The kernels for Roberts operators are this kernel and this kernel. This is gx and this is gy. Suppose this is an image and we want to calculate gradient at location p1 using Roberts operators, then we keep gx here and we compute gx, and we keep this gy kernel here and we compute gy, and we add those two to get resultant gradient. Suppose if we keep here, then we will get mod p1 minus p4, and similarly if we keep here, then we will get mod p2 minus p3. So resultant gradient will be mod g equal to mod p1 minus p4 plus mod p2 minus p3. Similarly, we have Sobel operators. Suppose this is our image and this is x direction and this is y direction. If you are intended to calculate gx and gy, then gx is given as using this kernel and this image. If you want to calculate gradient at the position z5, then we keep this middle pixel on this pixel and we multiply corresponding pixel values, and we will get this formula, which is simply z7 minus z1, 2z8 minus 2z2 plus z9 minus z3. Similarly, we have gy. Here, by looking at the direction of zeros, we can tell whether it is a horizontal edge detector or vertical edge detector. Here zeros are present horizontally, so if there is any horizontal edge in this image, then we can able to detect. And if there is here zeros are vertical, so if in our image there is any vertical edge, then this kernel will detect that. Resultant gradient will be mod gx plus mod gy. Here sum of pixel values in the kernels are 0. So if gradient is 0 in an area of constant intensity, because sum of kernel values is 0. The idea behind using a weight value 2 in the center coefficient is to achieve some smoothing by giving more importance to the center point. Then we have private operators also. There we have 1 here instead of 2, but Sobel operators are more used because these achieves some smoothing by having 2 here, by giving more importance to center pixels. So by using this resultant gradient formula, we can calculate resultant gradient by using Sobel operators. This is a horizontal edge detector, but why is this an horizontal edge detector? Because we are actually calculating correlation here, which will be maximum if both patterns are similar. Here the output of gradient is maximum if there is a transition from high to low or low to high intensity in our original image in a vertical direction, in this direction. because then our pattern will be in maximum resemblance with the original image, so it will lead us to maximum output because it gives maximum absolute value of gradient, thereby detecting an edge. Similarly, we have vertical edge detector. These are the steps to calculate gradient. Pad corners of the image with zeros so that gradient can be calculated to corner pixels too, and apply horizontal edge detection kernel at each point of the original image. Similarly, apply vertical edge detection kernel. Then add outputs of step 2 and step 3 pixel by pixel mod gx plus mod gy at each pixel. Then set a threshold and make gradients above the threshold as white and gradient below that threshold as black. Then edges can be seen using white pixels, and if there is no edge then it will be black. Suppose this is our image and we calculate gradient of this image, then gradient sharpens the image so it is helpful in detecting defects and to eliminate slowly changing background features. This is because in this image here, if we keep our kernel here, and as our kernel sum of values in our kernel is 0, so around these slowly changing background features our kernel will give 0 output. That is, we have black in our gradient image, so here we can see a completely dark here. Similarly at this outer region also, but during the transition it will have something because here there are edges, so these edges are going to be detected by our kernels, so we have this image in our output. By looking at these two images we can easily say that the defect in the image can be easily found in gradient image than in our original image, because due to varying background features, so gradient sharpens the image so it is helpful in detecting defects and to eliminate slowly changing background features. And also if we calculate negative of an image, then we can see that this does not give any much information about this defect, because negative of an image just flips whites to blacks and blacks to whites, but these slowly varying features are not removed, so negative of an image is not helpful in detecting defects because it is just an image of intensity reversals, so it will not make the image sharp. Here we can see both the negative image and image gradient. Like by looking at these two figures we can clearly say that image gradient tells information about defective edges, but negative image does not give any information. This is the MATLAB code to generate negative of an image. First we import the image, then we directly flip the values, then we will get negative of an image. From the pictures it is clear that image negative only flips the values, so it is not helpful in detecting sharp edges. Image negative calculates gradient at each pixel, and gradient can be used to enhance defects and eliminate slowly changing background features, and gradients are used to detect edges. Thank you.